This week's STEP question is from 2019, Step 1, Question 1. This question is a nice starting question, which includes trigonometry and some minimization. So the idea of the question is this, that we have a point 1k in the first quadrant, so k is positive. We have a line through the point 1k with a negative gradient, and we're going to minimize the area and also the perimeter of the triangle. Useful preliminary material for doing this question would be coordinate geometry, trig identities, especially those involving sec, cosec and cot of x, and differentiating trigonometric functions. Recall that STEP papers now don't allow the use of any formula sheet, so all identities used must be known, and the same for differentiation. So the question tells us, first of all, that we have the point 1k, and the gradient is minus tan of theta, and we're being asked, first of all, to find the points x and y, where the line cuts the axes in terms of k and theta. So the line will be y take k equals minus tan theta times x minus 1. Put x as naught, we get y equals k plus tan theta. Put y equals naught, we get x equals 1 plus k cot theta. Cot theta is defined as 1 over tan theta. You could write k over tan theta in this question. That would be perfectly valid. But since this question involves sec, cosec and cot all the way through it, we might as well start using those functions right from the start. So the next part of the question asks us to find a formula, an expression, for the area of the triangle OXY, where O is the origin. So using a half base height, we get a half 1 plus k cot theta times k plus tan theta. That will get us the mark. A simplified form might be useful for the next part of the question. So multiplying out the brackets, we get a half 2k plus tan theta plus k squared cot theta. The next part of the question wants us to minimize the area of the triangle as theta varies. So we differentiate the expression for area dAd theta. K is a constant, so that differentiates to naught. Tan of theta differentiates to sec squared, and cot theta to minus cosec squared of theta. If you're taking a STEP exam, these are results you really want to know. You don't want to be spending time in an exam working out these results from scratch. So the minimum value will be when the differential dAd theta equals naught, which gives us sec squared equals k squared cosec squared theta, which we need to solve. At this point, inverting the two and using sine over cos equals tan, we get tan squared theta equals k squared, so tan theta equals plus or minus k. We were told at the start that tan theta will be positive because theta is between 0 and pi over 2, and k is also positive, so tan of theta equals k. We don't need to justify minimality in this question, that's given to us, so we put tan theta equals k back into the formula for area and find that the area equals 2k. So the triangle with minimum area is when tan of theta equals k. In other words, the gradient is minus k, and the area then is 2k. The next part of the question now wants us to do the same thing with the perimeter of the triangle, OX plus OY plus XY, and we're going to minimize that. Slightly more difficult to do that because we need to use Pythagoras to find xy. So we've been asked to show that L equals a certain expression. So using Pythagoras, we have OX plus OY plus XY, and XY will be found using Pythagoras to be the square root of OX, 1 plus K cot theta, and OY, K plus tan theta. We need to simplify what is underneath the square root sign. We already have 4 terms of the expression we've been asked to find, so the job here is to use trig identities to simplify the expression under the root. So first of all, expanding the brackets using the binomial expansion. We then look at the 6 terms we've got. We have a 1 plus tan squared, which hopefully we recall to be sec squared theta. We have k squared times 1 plus cot squared theta, which hopefully we recall to be cosec squared theta. And we have 2k times tan theta plus cot theta, which simplifies to sine theta over cos theta add cos theta over sine theta, or sine squared add cos squared over sine theta cos theta. So this becomes sec squared theta add 2k sec theta cosec theta add k squared cosec squared theta, and this is the point at which we recognise that that is a perfect square. So it is sec theta plus k cosec theta. Our expression is, we have these 6 terms required. It becomes 1 plus tan theta add sec theta add k, 1 plus cot theta add cosec theta as required. This is a show that question. We've got to make sure our steps are clear to the examiner. We're now going to minimize this expression, and we've been asked to show that the L will be a minimum at angle alpha, where k equals 1 take cos alpha over 1 take sine alpha. So differentiating L, we get dl d theta equals sec squared theta add sec theta tan theta add k minus cosec squared theta minus cot theta cosec theta. The minimum point will be when dl d theta is naught, so sec theta add sec theta tan theta equals k cosec squared theta add cot theta cosec theta, which gives us an expression for k, which we need to simplify into the required form. So at this point, I'm replacing sec and cosec by sine and cos, because that's what we require in the answer. We have sine squared theta over cos squared theta, 1 plus sine theta, 1 plus cos theta. Replace sine squared by 1 take cos squared, and cos squared by 1 take sine squared, and then we can cancel to give the required answer. The required answer actually wants alpha. That's the required value to give us k. We now need to go back and substitute that k value in, 1 take cos alpha over 1 minus sine alpha, and simplify to find the minimum value of the length. So there is our expression. I'm replacing k by the expression we just found and putting everything into the form of sine alpha and cos alpha. I've gone for common denominators on the left hand side and on the right hand side, and what I'm going to work towards is common denominators all the way through. So notice that cos alpha add sine alpha add 1 is in both parts of the expression, so I've taken that out of brackets, and inside brackets I've got 1 over cos alpha, 1 take cos alpha over 1 minus sine alpha plus 1 over sine alpha. In workings like this, it's acceptable to use C for cos and S for sine, provided in the answer you write it out in full. So I've done that. The expression within the brackets simplifies to C plus S take 1 over CS 1 minus S. Then multiplying out the numerator, we get 2CS, and on the bottom CS 1 minus S, and that all cancels to give us the final answer of the minimum value of L being 2 over 1 take sine alpha. The question's done. What can we learn from it? One thing to learn is speed and accuracy of manipulation are essential to questions like this. You don't want to be spending lots of time manipulating your algebra and making false starts. You want to spend your time on thinking about the strategy for the question, not about the algebraic manipulation. Secondly, step questions now have no formula sheet, so you need to know the formulas in this question. Another point I would make is you could, throughout this question, in theory, have turned everything into sines and coses, but that becomes unwieldy. Far better to become fluent and confident in using sec, cosec, and tan. This was quite a nice, accessible first question for a step paper, not using much beyond A-level techniques, except the algebra is more complex because it's expressed in terms of alpha and theta. That's it for today. I'm David Forster. This is Gold Standard Maths, Saturday's Step Question.